Here we give brief description of solutions to the homework problems for Chapter 1 Introduction. For honor statement, you don't have to write long, just one sentence confirming you have read the requested sections, and don't kid yourself. Homework 1.1. So what do we have? We have two solid cylinder. One is DE, one is EF. They are bonded together at E and bonded to the solid base at F. We know the diameters for DE is 30 millimeter here and 15 millimeter here. Given the load condition as illustrated, a centric pulling force at the top D, F1 is 30 kilonewton, and the two forces F2 and F3 in a plane of symmetry uniformly distributed at E point, both pointing downwards. So we want to calculate the average normal stress. When we say normal stress, we mean the stress when the force and the plane of interest are perpendicular to each other. At the midsection for rod DE, somewhere here, and at the midsection for rod EF, somewhere here. So we know the loading condition situation, we know the geometry, especially the diameters. We want to know the average normal stress. That is our problem. So for the first part, for section DE on the top, I shrink the plot a little bit to show it here. And typically, to do this, we have to go back to statics and draw free body diagram. Let's cut arbitrarily between D and E, and this is what we have. Okay. On the top, of course, we have the F1, 30 kilonewton pointing upwards. So it is now balanced, which means at the cross section where we cut, we would need a internal force to balance F1 for this arbitrary section that we choose. And this net internal force, we call it P. And from statics, you would know P would be equal to F1 would be 30 kilonewton pointing downward. So this is our free body diagram for the section from D to arbitrary center point that we cut. Okay, and we said the internal force P would be same in magnitude as F1, 30 kilonewton, but in opposite direction. And as you can see, P and F1 are trying to pull this arbitrary section longer, so we say it is a tensile force. As a result, the average normal stress within DE, I call it sigma D. Sigma again is for normal stress. D is within DE section, is force over area. And of course, this force P, internal force, is perpendicular to the cross-section area that we are interested. P is perpendicular to A. And what is P? We said P equals to F1 is 30 kilonewton, and area would be just the cross-section area for this cylinder ADE, and 30 kilonewton is 30 times 10 to the power 3 Newton, and the ADE is a circular cross-section, so pi r square. And what is r? We know the diameter is 30 millimeter, and 1 millimeter is 10 to the minus 3 meter, and divided by 2 from diameter to radius. Okay, and you would have an answer. And for the course purpose, I hide the answers here. And of course, you would have a positive number, meaning it is tensile stress. Then for section EF at the bottom, it is slightly more complex. I still borrow the schematic here and make a arbitrary cut. Make an arbitrary cut here between E and F. Okay, so we still have at the top F1 pointing upward 30 kilonewton, and then F2 and F3 in a plane of symmetry, both going down 62.5 kilonewton for each of them. So it is all? Of course not, because these forces would not be balanced. As a result, we would need an internal force at the cross-section where we made the cut. And here we would have a so-called net internal force P, which balance F1, F2, and F3. And based on statics and the directions that we draw, the F2, F3, and P we pointing downward, so we put them at one side of the equation. F1 going upward, we put it at the other side of the equation. And then we would be able to solve for P would be equal to F1 minus F2 minus F3. F1 is 30, F2 and F3 both are 62.5, meaning the P value we are going to get is minus 95 kilonewton. Minus 95 kilonewton. So it's a minus sign indicating the actual direction for P is instead of going down, it should go up. And the magnitude is 95 kilonewton. So this is what we said before, based on free body diagram or FBD for the section from the top all the way to where we made the cut, we would be able to get the P minus 95 kilonewton. The minus sign indicates its opposite in direction to go upward. Then the internal force would be compressive, because if it's going down, it will be tensile, but if it's going up, it pressing in, it is compressive. Okay, again, sigma EF. Sigma for normal stress, EF is within section. The average normal stress within section EF would be still internal force over area. And in this case, the force we said, if we take the number minus 95 kilonewton, and AEF would be the area for this cylinder, this larger diameter cylinder. 95 goes to the minus sign goes to the front. 95 times 10 to the minus 10 to the power of 3 Newton, pi r square, and r would be 50 millimeter divided by 2, and millimeter going into meter. And again, I hide the final answer, okay, for students' benefit. And that concludes the problem 1.1. Again, this negative sign would be for compressive. We draw it down tensile for positive, so we get a negative number. That means it's for compressive. Now it's homework 1.2. Here we said the link FH consists of a single bar 1 inch wide, 1 inch thick. That is for FH. And then we have this EFG bar with hinge connection at E and supported at F by this FH. And then we have the external force F1 of 40 kilo pounds of force. And we want to know the average normal stress in the middle of the bar FH if theta equals 0, which means pushing horizontally to the left, or theta equals 90 degrees, which means F1 is pushing vertically down. Okay? Let's first look at the situation when theta equals 0, which means the force F1 is pushing leftward, horizontally leftward at G. Okay, so to do this thing, we can consider the balance of moment around E for the EFG bar. We can first consider the balance moment around E for the EFG bar. So if we consider the balance moment, we don't have to consider whatever force at E, then we would have horizontal force pushing towards left, and then a vertical force, let's assume it's going down, exerted by FH at F point. Why is it exactly vertical? Because if you consider the FH bar, if we consider the FH bar, it is a so-called two-force body. It is a two-force body. FH is a two-force body, which means the force at the two ends must go along the axis for this FH. So as a result, the force has to go down. So if we have these two forces, then we can write the balance moment for 40 thousand of pound of force or F1, and then the distance from this force to the axis E would be 12 plus 6, totally 18 times this is 30 degree times sine 30 degree. Okay, that is the moment that try to rotate the bar counterclockwise around E. Meanwhile, for the RFH, we don't know its magnitude, but we know it is vertically down. So RFH times 12, this distance, times cosine 30 degree. 12 times cosine 30 degree would be the distance from E to this force. Okay, and this moment is trying to rotate the bar EFG clockwise around E. So one counterclockwise, the F1 force trying to rotate the bar. The other is clockwise, the RFH try to rotate the bar clockwise. And as a result, we can solve for RFH. The force exerted by FH bar on EFG bar would be 34.6 KIPS or thousand of pound force. Okay, then let's consider only the FH bar. Let's consider the FH bar. And we know the FH bar exerted the downward force on this EFG bar, which means if we consider FH bar, the EFG would be trying to pull it up. So if we make an arbitrary cut in the FH bar, the net internal force would be counteracting this RFH prime force. So P, internal force P, would be the same in magnitude as R prime of FH or RFH, which is 34.6 thousand pound. And so the average normal stress, in this case tensile stress, because it is trying to pull the FH longer. The average normal stress at the middle of the FH bar, note, not where the pin is, but at the middle where there's no pin, without that hole or pinhole, would be force over area, internal force, which is P, the rod normal cross section, it will be 1 inch by 1 inch, and then the internal force we just said it is 34.6 thousand of pound of force, and then as a result you would get the unit of psi, or you can also write it in KSI, means thousand of psi. Again, sigma for normal stress, average tensile is normal force divided by normal cross-section area. And this would be the formula to calculate the result. And I hide the result in this case. For the other part, when the theta equals 90 degree, then in this case, F1 is pointing downward, and the magnitude is still 40 kips, 40,000 pounds of force. Again, let's consider the balance of moment around E, And in this case, because we are considering balance of moment around E, any force at E are not considered or omitted because the distance from that force to the axis is 0. Then, similarly, as what we said before, the reaction force along FH bar would go RFH. I draw it pointing upward because F1 is trying to push it down, rotating clockwise. So I draw RFH and pushing up, trying to counteract, trying to rotate the bar counterclockwise. And similar as before, the FH bar would be a two-force body, which means the force RFH would be vertically along the bar axis. And then let's consider the balance moment. We still have 40 kips times the distance from E to this force. That will be 12 plus 6 times cosine 30. And that would be the moment trying to rotate the bar clockwise around E. On the other hand, this RFH is counteracting it. It times 12, this distance, times cosine 30 degree. And this gives us the RFH of 60,000 pound force or 60 kips. Okay. And if we draw RFH onto the bar EFG, pushing it up, then for FH, the EFG is trying to push it down, and if we make an arbitrary cut within FH, the internal force would be counteracting in the opposite direction, trying to push it up, and this would be our internal force. Of course, the magnitude would be the same as RFH prime or RFH, and it's compressive force because the internal force is pressing in. As a result, the average normal compressive stress at the mid of the FH bar, its absolute value would be P over area. P is the internal force. Area would be the normal cross-section area. It is 1 inch by 1 inch, and P, as we said before, is 60,000 pound force. And as a result, you can get the average compressive stress in the unit PSI or in KSI for 1000 PSI. Okay. Homework 1.3. We want you to determine the diameter of the largest circular hole that can be punched to a sheet of polystyrene 4 mm thick. Let's say this blue block is our polystyrene sheet, and the thickness from here to here is 4 mm. We want to know the largest circular hole that can be punched out by let's say a steel punch. The punching force is 22.5 thousand Newton or 22.5 kilonewton, and the average shearing stress of 55 megapascal. Shearing stress of 55 megapascal, MPa. Mega means 55 times a million pascal. Is needed to cause polystyrene material, cause this material to fail to cut through, for the punch to cut through and make a hole. So we want to know the largest diameter. As you can imagine, if the diameter is too large, the area would be too large and it will be difficult to punch out. Okay, so we give the hint. The hint is that the shearing force is acting along the side of this cylindrical punch, not the top surface, not the bottom surface, but the side of this cylindrical surface. Okay, and that is our so-called shearing surface. So the total area for this shearing surface for the side of the cylinder, as we learned in geometry, would be pi dh. Pi d, the pi times d, d is the diameter for this punch. Pi times d would be the circular length, circumference, times h. Is the thickness for this plate. Pi dh gives us this dashed cylinder in the hollow cylinder in this sheet with thickness of 4 millimeter, or h equals 4 millimeter. Okay, and the shearing stress, as what we learned, we know the shearing stress is 55 megapascal. Mega again means 10 to the power 6 or million. So shearing stress tau would be force over area, and force we know is 22.5 kilonewton. The area, the shearing area, which, as we said again and again, is the side for this short cylinder in the sheet. So it will be pi dh. D is again the diameter for this cylindrical hole, or diameter for this punch. They are very close. H would be the thickness. We want this whole ratio, this tau, the shearing stress, to be greater than 55 mega, means 10 to the power of 6 Pascal. So as a result, D, the diameter for the punch hole, would be moved to the other side, would be smaller than force over pi h. Force, we put in 22.5 times 10 to the 3 Newton. Pi is 3.14, and D would be smaller than pi divided by pressure tau, and the h, which is the thickness for the plate, it's 4 times 10 to the minus 3 meter, or 4 millimeter. Remember, 1 millimeter is 10 to the minus 3 meter. So we have Newton in the numerator, Pascal in the denominator, but Pascal is Newton over meter square, and over meter square goes to the numerator, and the meter square divided by meter, we will have meter. So I leave the answer open for your own benefit. Thank you. Homework 1.4. It's a simple one. We said two rectangular glue wooden parts are bonded together as illustrated. One part at the top, one part at the bottom, and they have both a flat surface, and they are glued together as illustrated along the flat surface. Each of the part is 2 inches long and 1 inch wide. We didn't specify the thickness, which means it may not matter here. And a pair of shearing forces, P are applied to the bonded pieces in the plane of symmetry. I should have mentioned they are in the plane of symmetry. And when the shearing force P reaches, or P prime reaches 1600 pound force, when the shearing force P or P prime reach 1600 pound force, the two pieces started to separate or fail along the bonding interface. One goes to the top piece, moves towards the left, the bottom piece moves towards the right, and they start to separate or fail along the bonded surface. Then we want you to calculate the average shearing stress. The average shearing stress at the time of failure, when the interface starts to fail, when the top and the bottom start to separate and slide against each other. So it is very simple. We use the definition for shearing stress. Tau again means shearing stress would be force over area, except now the force F or P here are parallel to the area that we are interested, which is P horizontal, P prime horizontal, and the area of interest is the flat surface between these two pieces, and they are flat. And the area would just be for that area of interest would just be 2 inch times 1 inch, or 2-inch square, and the P or P prime would be our externally applied force, and then we said that is 1600 pound of force, So then you plug the number in, you would be able to get the average shearing stress in these two pieces at the time of failure. Similarly, I hide away the unit and the number for your own benefit. Again, PSI means pound per square inch or pound force per square inch. Homework 1.5. Again, it's very similar to our class examples. Two wooden pieces of uniform square cross section. So the cross section on this side or on the other side would be square with edge length of 1 centimeter. So from here to here is 1 centimeter, from here to here is 1 centimeter, from here to here is also 1 centimeter. Joined by gluing along an oblique interface, not 90-degree, but at a 60-degree flat interface, and shown. So if the tensile load is 10 kilonewton, P on the right 10 kilonewton, P prime on the left 10 kilonewton, we want you to calculate the normal and the shearing stress for the glued oblique interface as illustrated. We want to calculate the normal stress and the shearing stress for the plane of interest along the glued interface as illustrated. Okay, so here I copied our schematic, and then I have a side view for one part, for let's say the left part. Okay, we would have P centric force, but then the P could be resolved in the normal direction and in the shearing direction. So if this angle is 60 degree, which means here we have 60, and then here the angle from normal to the axis would be 30, because 30 plus 60 would be 90. Okay, so the angle from the normal of that oblique interface and the horizontal axis would be 30 degree. So the normal force Fn, F for force, N for normal force, would be P times cosine 30 degree. And if you plug in a number, you would get 8.66 times 10 to the power of 3 Newton. And the shearing force, Fs, the shearing force, as you see, would be P times sine 30 degree. And it would be 5,000 Newton. And then the total area for this flat oblique interface, A theta would be A0, the normal cross-section area, divided by cosine 30, because this angle would be 30. A0 divided by cosine 30, or 1 centimeter square divided by cosine 30, we know it's 0.866. And then the area would be 1.155 centimeter square. So the normal stress, when the force you are considering is perpendicular to this plane, would be Fn over A theta. Fn we said is 8.66 times 1000 Newton divided by A theta is 1.155 centimeters square, and you plug in the number, you get the answer. Similarly, the shearing stress tau would be shearing force Fs divided by the area for this oblique interface, the area of interest of A theta, and that is 5000 Newton divided by the same 1.155 centimeter square, and you get the shearing stress. And I hide both of the for your own benefit. Again, the angle from the oblique plane to the base is 30, which means from the oblique plane to the vertical, it would be this angle would be 60. So from oblique plane to the vertical would be 30. Okay. So either way, you should be getting the answer that we showed here in the answer and hints slide. The last problem from chapter 1.6 it's related to statics, but using what we learned. So members of DE, EF, and the DF of the truss shown are made of the same material, which means it is known that the material has ultimate tensile strength. Sometimes we call it the sigma U, U for ultimate, sigma ultimate tensile strength, the highest stress level above which the material will break or fracture for sure is 200 megapascal. Okay, if the safety factor is 3.0, again the safety factor is the ratio between ultimate tensile strength and the allowable stress. Is 3.0. If the safety factor of 3 is to be achieved for both DE and the DF bar, here we only consider DE and the DF bar of a safety factor of 3. We want you to determine the required minimum cross-section area for bar DE and bar DF. As you can imagine, if DE would be too small in cross-section area with 10,000 Newton or 10 kilonewton of force, you may well break the DE bar. For the same reason, you may also break the DF bar. So how do we solve this problem? What do we want? We want the minimum cross-section area. So let's solve the problem part by part. This is our schematic: DE, EF, DF, and truss. Hinge connection at D and on a roller at F. Okay, let's first consider for bar DF. For bar DF, what would be the area cross-section area requested for bar DF? So we have an external force of E trying to drag down as well as try to rotate it clockwise. Let's consider the balance of moment around the D point. The balance moment around D for the entire DEF truss. For the entire DEF truss. The external force 10 kilonewton is trying to rotate it clockwise. So 10 kilonewton times the distance from 10 kilonewton to D would be as what we give here, 0.75 meter. That is the moment that tries to rotate it clockwise, and it is counteracted by Rfx, the reaction force at F point along horizontal or x-axis. Because it is on a roller, that would not be vertical reaction force at F. Okay, and we also neglect any forces that passes through D, reaction force at D, because the distance from those forces to D point would be 0. So the only thing that counteract this 10 kilonewton rotating clockwise would be this reaction force horizontally or along x-axis, and the distance from D to that horizontal force would just be this 1.4 meter. So from here we can solve for the reaction force in horizontal direction would be 5357, and it should be pointing to the right. Okay, so we solved one part of the puzzle. We know the force. We know the force at df along df. Then, as we learned, the df bar hinge connection, D hinge connection at F, it is a so-called two-force body rod, which means the net force at D and net force at F must go along the rod axis, and they should counteract each other. So the two forces along DF, whether it's going upward or the other force, the net force going around DF must satisfy for, if we consider F point, they must satisfy this relationship, which means the FDF for F point, FDF is trying to drag it up. The RF for F point, FDF is trying to pull it up. The RFX is trying to push it to the right. And meanwhile, the EF bar gives another force. FEF is trying to push F in along the raw direction. So these three forces are in balance at F point. Okay. And then as a result, this triangle and the geometric relationship are similar triangle. As a result, FDF here or here divided by RFX here versus here would be similar to the distance from here to ratio here. From E to F vertically, that is 1.4 total minus the top 0.4. That is the vertical distance from E to F. And then the horizontal distance is just from here to here. From here to here is similar, it's just a 0.75. So 1.4 minus 0.4 is 1 divided by 0.75 is 4 to 3. So if we know RFX is 5357, we can know that FDF would be 4/3 times this RFX, and it end up to be 7,143 Newton for FDF. For FDF, the net force here would be 7,143. So we want the safety factor to be at least 3 or greater than 3. Factor of safety would be ultimate tensile strength divided by allowable stress. And the allowable stress would just be, for this DF rod, would be the force over normal cross-section area for DF to be greater than 3. As a result, because here the ADF is in the denominator of the denominator, so you flip it up, so we would have ADF, the area normal cross-section area for DF would have to be equal or greater than 3 times FDF divided by sigma u, our ultimate tensile strength. 3, keep it in the front. FDF, we just calculate 7,143 Newton divided by the sigma u, ultimate tensile strength is 200 megapascal, 10 to the power of 6 Pascal. And if you plug the number in, you would get a minimum cross-section area for DF. Okay, again, how did we solve this problem? We first use statics balance of moment to find out the force RFX. RFX, the force horizontally pushing F out and trying to make the triangle rotate counterclockwise. And then we said both DF and EF are two force body, which means the net force at two ends must go along the rod axis, okay? So which means this FEF must go along the rod direction. And then the FDF to RFX, the ratio should be satisfy this triangle, and that should be similar to this geometric triangle. And what is this geometric triangle? From E to here, it's 1.4 minus 0.4 is 1. From here to F, it's 0.75 meter. That's what we said. And as a result, we can calculate from RFX the FDF, the net force along DF. And then if we know the safety factor, we can know the minimum cross-section area for DF region. You may ask, why don't we calculate EF? Well, that maybe it doesn't matter, or maybe it's a different material that is much stronger, so it is not calculated here. For the second part, for body E, from previous we already know the Fx, Rfx, the reaction force at F along horizontal direction is 5357 Newton. Then for this whole DEF, if there's a reaction force at F pushing it right, then as a result, there should be a reaction force at D pulling it in. RDX, R for reaction force, D at D point, X means horizontal, would be same as magnitude of RFX, and it will be 5357 Newton, and it will be you are pushing it away, and for the top it has to drag you back, going to the left. Then DE is a two force body. Similarly, DF is a two force body. Then if we look at D point, the balance force at the D point, RDX trying to make it to the left, RDY try to counter the FDF going down. And we also have the FDE. FDE is trying to drag the D point along its this oblique direction. Okay. It looks complicated, but let's focus. What do we want? What do we know? We know RDX. We already know RDX. What do we want? We want the force along DE, FDE. So as you see, the RDX over FDE, RDX, which is also the same over FDE, would be the cosine for this theta, and it would be 0.75 divided by 0.75 square plus 0.4 square, this distance. Okay, and if you plug the number in, the FDE would be the square root over 0.75 times the RDX, and RDX is 5357, and in the end you would get the FDE, the force along DE, internal force would be 6071 Newton. Similarly, factor of safety is at least 3, so factor of safety is ultimate strength over allowable stress. Ultimate strength is 200 megapascal, and allowable would be the force FDE over AD. So what you want AD would be greater than 3 times FDE divided by sigma u. And FDE, we just calculate 6071 Newton, and sigma u is 200 million Pascal. Okay, and the Newton over Pascal, which is Newton over meter square, become meter square, and you plug the number in, you get certain meter square or certain millimeter square. Okay, and I hide these for your own benefit.